All right, people, today we're going to be talking about effusion and diffusion. Now, these concepts are based off of the kinetic molecular theory. It's based off the physics. It's based off of the um, the equations that we kind of didn't really look through. We talked about them a bit. Um, but let's just talk about effusion and diffusion. Now, diffusion is the mixing of gas particles. It's the mixing of gases. So common examples of that would be your cologne, cooking. I don't want to say it, but you know what I'm thinking about. All right. Yeah. So these gases, whenever they're released, they eventually spread across the room. They diffuse. They spread across. They mix evenly with the air. This is just something that gas particles do. It is in their nature to do it. Their randomness eventually leads them to be mixed up. All right. Now, so let's talk a little bit about that. The gas particles and what really changes their speed. The number one factor that affects the speed of a gas particle is the heat. The hotter the particles, the higher the velocity is going to be, and that's why when you look at this black graph right here, that black graph represents the higher temperature. So the majority of the particles have a higher velocity. So the majority of the particles are shown by the peak. This peak is at a higher number. So more heat equals faster particles. If the particles move faster, they mix faster. And yeah, that's just kind of what this graph is showing. It's just showing the differences between or the relationship between temperature and average velocity. Since we can't really study individual gas particles in a practical way, we like to think of them as an average of all their particles together. All right, now let's talk about Graham's law of diffusion. Now that we're done with that, this one actually has. Wait. So the effusion, I like to think of E as an escape, as in leaving. So the escaping of a gas, and the way you can think of that is a balloon, right? Everyone's gotten those birthday balloons, and you don't want to throw them away because someone gave them to you, and you eventually the balloon looks all sad and wrinkly and droopy, and you throw it in the trash. The reason why that happens is because there's tiny little holes in your balloon, and there's tiny little holes everywhere. Gases can leave. So the rate of effusion is, well, it's determined by how often the gas particles leave through tiny little holes. Now let's say there's just a hole right here. And if you have a very small particle, a very light particle, then you have a very heavy particle. Well, the small one is going to be able to move quicker. And if it's able to move quicker, chances are it's able to go through the hole a lot faster. So the rate at which something leaves, or the rate at which something escapes, is related to the size of the atom. The smaller the atom, the faster it leaves. The larger the atom, the longer it takes for it to escape. So the equation we get is this right here. The rate of diffusion for gas 1, right here. And then the rate of diffusion for gas 2 at the bottom. And then you have your M's right there. Now, this big M is your molar mass. But it doesn't have to be in grams or kilograms. It can be in whatever. It doesn't matter as long as it's molar mass, because the units are going to cancel out. It's grams over grams, kilograms over kilograms. So that makes it very easy on us. All right, so let's look at a problem, and this problem is it's on page 197. Page 197. Example 5.20. All right, calculate the ratio of effusion rates of hydrogen gas and uranium hexafluoride. Uranium hexafluoride, a supermassive gas, and hydrogen gas, the smallest gas. So the smallest gas has a way higher average speed, and the heavy gas has a much slower speed. If we compare the masses, because we need both, remember it's rate of, let's just say, the rate of hydrogen over the rate of UF6, and it was related, or it was proportional to the mass. So if hydrogen is on top, that means the molar mass of hydrogen is going to be at the bottom, and then the molar mass of uranium hexafluoride on the top. So this is always a ratio. So we're just going to put R over RH over RUF6. It's going to equal the molar masses. So the molar mass of UF6 is 352.02 grams per mole. And then over here, 2.016 grams per mole. You divide both of these and then take the square root. So 352.02 divided by 2.016, and then let's take the square root of it. Hello? And we get 13.2, no units. 13.2. What does this 13.2 mean? What this 13.2 means is that hydrogen is 13.2 times faster than UF6, than uranium hexafluoride. Does that make sense? I hope it does. And these problems are, that's as complicated as it gets, honestly. The rate of diffusion, uses the same formula, it's based off of the distance traveled. So there's an experiment where you use a burette. Pretend that's a burette. Pretend that's good. That's a good instrument, and it's not all. If your burette looks like that, your school needs a better budget. All right, so my burettes look like that. So you have a piece of cotton on each end, right? And let's say you have HCl concentrated and then NH3 concentrated. Well, the gas particles are going to move in here depending on their molar mass, and they're going to travel a certain distance. That's what you're going to put as your R's. Instead of the rate, you're going to write your distance traveled. But I'll probably make a separate video for that because it is a lab. And I still haven't really worked on lab videos, but we will take care of that later. All right, but that's it for now. Take it easy. And that's it. We'll see you in the next section when we talk about the real gas law. Peace out, people.